live streaming settings. So once after that, I'll make you a host.
Sure.
Yeah, Professor Lok, I have done that setting.
Thank you so much.
Yeah, welcome.
Maybe we wait a couple of more minutes.
Yeah, we can wait for a couple of more minutes, Professor Lok. Actually, today is, you might be knowing, Holi, it's here. Holi.
Yeah, I saw that on Facebook. I didn't know that before.
So
Yeah, your life
I think everyone
has
is
been
celebrating
crazy.
that, and then getting out from the holiday mood to the regular mood. I think it is pretty difficult, it seems.
Oh, okay. So students are in the university, or they are
This
attending
is
from
part of
home?
university, and then part of them are outside. So,
Okay.
as it is a pan India thing, so people from other states have also joined. So,
Okay.
from the neighboring states, and then which includes both students as well as the scholars as well as faculties, but not in huge number as we are there in the middle of the semester here. So most of the
Okay.
universities go for final in some exams, or they are in a process of completing the syllabus, and then
Mhm.
lot much of time has been wasted uh, because of shifting from online to offline classes, because they need to have a 14-day window for isolation or 7-day window. So it took for
Okay.
most of the universities time crunch. So they are coping it up.
Yeah, it's good that COVID is perhaps going away, right?
Yeah. That is one such good thing. So thank God that there is no second or third variant or fourth variant that is coming out from Omicron. And then now I think
Hmm.
slowly India has moved on. There's a big election that went on, so the election results are out, and then mostly the India is now going back to normalcy.
That's good.
How is the condition there?
Yeah, I think it's getting better. So they removed the mask mandate here as well in the university too.
Okay. Uh,
So
okay, good. Actually, here the mask mandate is still there, but still
okay.
people are feeling safe without the mask itself. But the instructions
Yeah,
are
yeah. I understand how it works. Yeah, I mean, we had a habit of using masks, and then now all of a sudden, no mask, so it feels weird now.
I feel it's really relaxing after that. You see, there are so many variants of masks, N95, and then this cloth mask, and then surgical masks, and then so many permutation and combinations were there at the peak time. So now I
Right.
feel it's okay.
I have a question for you. Quick question
Yeah,
before we get started.
yeah.
So in India, is there a central government or something like that that collects mask use data as well as COVID-19 cases and death rate?
Uh, as of such, no such agency collects that, because still convincing people to wear mask itself, it took for the government so long time. But there is no such mechanism to collect those. But again, uh, partly ends in solid waste and partly ends in biomedical waste. So there is no such single agency which
Uh-huh.
has the data over the mask usage, and then the
Okay.
so in that case, if you need that kind of thing, then I will look for it, and then let me see if any of the private agencies are. I am in touch with a couple of managing facilities here in the state, and
Uh-huh.
then if you have something in your mind, and then I can just check whether they collect those, and then the aftermath what they do, and then everything. So I'll get back to you. But as of now, on a pan India level, there is no such mechanism. That I'm pretty sure.
Okay. Yeah, I think that would be very helpful. I have one of my doctoral student, and she's looking for some data, and we currently have access to one national database, but before we requested the data, we didn't know they didn't have the max data. So we are hoping that there will be some max related data for different counties and different cities in
Okay.
different states. But yeah, she's interested in looking from environmental health and safety standpoint, how the
Okay.
max use or not used depending on the max mandates in certain counties
Okay. So
may have.
actually, you need
Yeah,
quantity of masks that gets into the waste managing facility per day, or what kind of information?
that's interesting. Yeah, I mean, if there is, well, any kind of data might be useful, right? But we were looking for, like, in the US, each county has its own authority whether or not to mandate the mask use. So based on those information, if a county has a mask mandate in place, how was the rate or the cases of COVID versus the other county or neighboring county where there was mask mandate or no mask mandate, and how the cases and the death differ. Probably it will not be cause and effect, but it could be some kind of correlation.
Okay, okay.
Yeah.
So I'll check and then I'll get back, Professor Low.
Sure, sure. There is no rush. Yeah, please take your time. Okay.
Yeah.
So we have 11 participants, and it's
I
11.
think we can start by the time I think slowly. I have also dropped a message to all, so I
Okay.
think slowly join. I feel, but by the time we can
Yeah.
start.
I know it is final day, so and it's holy there. So
Yeah, it's a holiday. I also completely when we proposed it 17th because as there was a mandate to complete it before this financial end, so
okay.
everyone knows that. And then so I didn't know that 18th falls on a holy. So once I kick-started the program, then I came to know that 18th is the last day is a
Okay.
holy day.
Okay, I understand.
Okay,
All
okay.
right. Good morning, everyone. Welcome back. So the final day of the GIAN course series. I hope everybody is learning something new and finding it useful. So today we have two lectures. First lecture maybe a little brief, then the second one. So probably as we finish the first lecture, maybe we'll have 5 or 10 minutes of Q&A and maybe take 5 minutes break, and then we'll start and get the second lecture or the final lecture done. So with that, again, welcome back. So the topic of today's presentation, lecture 7, is antimicrobial engineered nanoparticles or nanomaterials and nanomicrobial interaction. So this portion of the lecture will mainly focus on E. coli results or data and how nanomaterial may interact with the E. coli cell surface, resulting into toxicity. And again, in this part of the presentation too, I'm showing our own data, and the data for this presentation is currently under review. So we just revised and resubmitted the paper to the Scientific Reports journal, which is a really high impact journal. So a general overview. So we'll decipher nanobio interaction and related toxicity on E. coli. And again, the examples will be on nano silver. And also towards the end of this first part of the presentation, I have few slides, couple of slides on how we can improve the efficacy of antibiotic drug using the nanoparticle. And in the second part of the lecture, we'll be talking about, I'll walk you through the major steps involving human health risk assessment, or rather risk assessment. In the literature, you will find the term human health risk assessment, but the real technical term would be risk assessment. The US EPA, as well as National Academy of Sciences, or National Research Council of National Academy of Sciences, they tend to use the term risk assessment, and which seems to be more technical than saying human health risk assessment. Generally, I claim myself to be a risk assessor as well, because I had extensive training doing risk assessment during my PhD education, and we have also published a couple of papers doing risk assessment. One being on electronic cigarette, and we look at one of the component in electronic cigarette and did the risk assessment. We have also published a paper on isoflurane. Isoflurane is an anesthesia that is used in the hospital and veterinary clinic. And we use similar approach in both of those papers using established US EPA or National Academy of Sciences risk assessment framework. So I'll be walking you through the major steps involving risk assessment as used by US EPA and originally published by National Academy of Sciences of the United States. I know Dr. Dubey has covered some portion of the risk assessment, and thank you so much for Dr. Barindaran for sharing the video link, so I was able to go through the video and try and as I was preparing my slides, because I didn't want to overlap too significantly, because that's going to be boring if we present the same information twice. So with that, let's get started. So here we are looking at the nanoparticles that we use for this study, And again, this is nanoparticle characterization using TEM on the left panels, and on the right panel we have EDS spectra, suggesting the particles are made of silver, and we have particle size distribution here. So the top particles again are amino silver nanoparticle, which we have seen before. It's the same particle, and the bottom particles are citrate coated silver nanoparticle. So it has a very nice uniform citrate coating on the surface, and similar uniform layer of amino group is present on the smaller size particle as shown here in panel A. And on the bottom panel A and F, we are looking at EDX spectra and particle size distribution respectively. So the citrate silver nanoparticles are about 45 nanometer size. You may have observed or noticed slight difference in these sizes for the same particle because as I mentioned earlier in our presentation, as you run the electron microscopy analysis for different batches, you will tend to see some minor variation, and we tend to stick with the same analysis for that specific batch that was used for the toxicity testing. So first, we will look into the growth curve for E. coli, and we use the strain E. coli K12, which is a very common laboratory strain. So I'd like you to focus on the plot on the right. So here the red bar, the red scatter plot is for 10 ppm, which is 10 milligram per liter or 10 microgram per milliliter of amino silver nanoparticle. So what we are seeing here with this red scatter dot or scatter plot is that initially up to 4 hours we saw some growth, and we call this the acclimation state for the bacteria. But after that, the bacterial population declined significantly, and that was close to or equal to the initial population that we started. But the initial population, what you see here is the background corrected population density. Obviously, it is the observance value that we measure at 600 nanometer using the UV spectrophotometer. But when you see a plot like this going down, it indicates there is bactericidal effect. So with 10 ppm amino silver nanoparticle, we claim that in this paper that our particles at 10 ppm are bactericidal. And here at the bottom is silver ion. So from the start, with the silver ion, there was no growth. When the scatter dot or scatter plot is more or less a straight line, it is referred to as bacteriostatic. It didn't grow at all. So what we can say is, and for silver ion too, the concentration we used was 10 ppm, at least for this plot. We also use 0.5 ppm for both amino silver nanoparticle as well as silver ion. In addition to that, we also tested citrate silver nanoparticle at the same concentrations. And the black scatter dot is for the control sample without nanoparticles. So the control samples will have algae broth, which is the nutrient media. So citrate silver nanoparticles at both concentration, lower and higher concentration, were non-toxic. And what we also saw interesting with citrate silver nanoparticle was the green line here, the green scatter plot at the top, that is for 10 ppm. So at highest concentration we tested, the growth was almost close to the control. But at lower concentration of citrate silver nanoparticle, which is 0.5 ppm, which is the blue line here, the growth was lower than at 10 ppm. So at lower concentration, growth was lower. You would expect higher growth, meaning that lower toxicity. But here the trend for citrate silver nanoparticle was opposite. This might suggest that actually bacteria may be liking more amount of citrate on the surface of silver nanoparticle. Remember, there is a citric acid cycle that is involved in the respiration of living organism. So perhaps citric acid or citrate might be favoring the growth. So excess citrate favoring higher growth and less citrate favoring lower growth, which is what these two plots for citrate silver nanoparticle indicate. Although we did not talk about that in the paper, we just wanted to stick with the amino silver nanoparticle because our interest is for the application purposes to mitigate bacterial infections in the hospital in the patients. Ultimately, that's the goal. Uh, but looking at the biology of citric acid or citric acid cycle, there is potential that bacteria might be using citric acid or citrate on the surface of silver nanoparticle for respiration, and therefore there is less toxicity. So in these plots, we are looking at phenotypic changes or phenotypic alteration in E. coli, which means morphological changes. So under the electron microscopy, in a moment, I'll show you electron micrographs um, of the same plot or for the same plot. So what you see here is different color represent different cluster or different treatment groups. So with different treatment, again, the treatment is same as like the previous slide. We observe different size E. coli cells. So the same thing here is plotted on the plot on the right, plot C. Length of the bacterial cell is plotted on the top panel and the diameter is plotted on the bottom panel. So you do see a variation in the length and also slight variation in diameter. At 10 ppm of amino silver nanoparticle, you don't see any plot because all bacteria were dead. We couldn't even locate a single bacterial cell under the electron microscope after repeated uh, analysis. So no cells were observed. That means they were dead, and this confirms our absorbance reading or the cell growth curve that we saw earlier. So these are the electron micrograph. The control is the A panel, top left. You see nice cells. Um, the green triangle shows the adherent fimbriae. Fimbriae are cilia of filamentous structure that allows the bacteria to move or locomote, as well as these fimbriae are used for cell-cell communication and biofilm formation. Remember, biofilm formation is a big issue in the hospital setting, especially with medical devices. So towards the end of this presentation, I will have a couple of slides and also will give you some background on hospital-acquired infection. In other words, hospital-acquired infection (HAI) is also referred to as nosocomial infection. So we have control cells here, very nice, with long fimbriae, and we see fimbriae everywhere. With amino silver nanoparticle at zero point 0.5 ppm, we saw cell damage indicated by red triangles, and we didn't observe any fimbriae even at this low concentration. With citrate silver nanoparticle at zero point 0.5 ppm, we did see fimbriae and we did not see observe any damage to the cell, so it is non-toxic, so which confirms our scatter plot earlier. With citrate silver nanoparticle 10 ppm, again we didn't see cell damage, we still saw adherent fimbriae. So our goal here in this project was to see if cell damage would occur as well as if there is inhibition of adherent fimbriae expression, meaning that if you can inhibit fimbriae expression, then perhaps you can control the biofilm formation in the medical devices and perhaps the organism would be less infectious. With silver ion at the bottom, uh, we do see fimbriae here. They are a little shorter. Uh, and in the insert here for the same sample E, at zero point 0.5 milligram per liter for silver ion, we did see a lot of cell damage indicated by red triangle. Now, what is interesting with this study is that the figure F. So in figure F, we have silver ion at 10 ppm. You see the morphology? The morphology has completely changed. So the bacteria assume the honeycomb-like structure, hexagonal honeycomb-like structure. We went back to the literature and studied what is there in honeycomb-like structure, what is important or significance of this structure, and we found that uh, honeycomb-like structure or hexagonal structure is the least energetic structure. So organism can use least amount of energy to generate this structure when they are under stress. So meaning that bacteria is stressed with silver ion, but they are not dead yet. With amino silver nanoparticle, no cells were located, and the scatter plot also indicated that there was steady decline after 4 hours, suggesting that amino silver nanoparticles were or are toxic or bactericidal. So this discovery is important for silver ion. In the hospital setting to treat burn patient, uh, still today silver salt or silver ions are used. Now this result of ours indicate that that may not be effective because the bacterial cells may not be completely destroyed, especially if a larger amount of silver ions are used. At lower concentration, however, though, we did see cell damage with silver ion. So the documentation of the honeycomb-like hexagonal structure, hexagonal honeycomb-like structure, is is a novel finding in this study. So this is just the table showing all of those results combined together. So we have different concentration here on the second column. In the third column, we have cell damage, yes or no. When they are dead, we reported dead. And in the second last column, we have fimbriae, present or absent. And in the last column, we have the shape, whether or not the shape of the cell were changed. So typically, the E. coli is rod-shaped. Uh, Now, with amino silver nanoparticle, we saw significant change, meaning that there was cell damage at zero point 0.5, at 10 microgram per mil, 10 milligram per liter. There were no cells, so they were all dead. Fimbriae were absent in both concentration, with both concentration, and in terms of shape, at lower concentration, we still saw a rod-shaped structure, but at 10 milligram per liter or 10 ppm, cells were dead. So this is a novel finding. Here we are showing the interaction of amino nano silver with the E. coli cell surface. Now what is interesting here is under the electron microscopy, which is FESEM, field emission scanning electron microscopy, at the two distal end of the cells, we saw this huge particle, or we can say an aggregate. Although it looks like a single particle, it could be an aggregate of those smaller particles, because these particles here, what we are seeing, are actually larger than what we added into the system. So we have 5 nanometer size particle to begin with. However, when it interacts with the cell surface and the biological components, it seems like the particles may grow and become bigger. Now, this sample was imaged after 10 minutes of exposure. Why? With 48 hour or 72 hours of exposure. 48 hours is typical duration or incubation time for bacterial study. We did study until 72 hours just to look at the difference in curve. So after 72 hours or 48 hours, since there were no cells, so we thought, let's expose for a shorter duration and quickly observe under the microscope. So we only expose for 10 minutes, right on the stub, electron microscopy stub, and then inserted the sample into the microscopy, and we found that these particles were the two distal end. And we did the EDX analysis, and we found that these two dots, which are very prominent and dense looking, point 10 and point 11 over here, corresponds to the spectrum 10 and spectrum 11. So they have high amount of silver. So at for point 10, spectrum 10, we have 0.8 weight percent of silver, and in spectrum 11, although to our eyes they look more or less same size, the EDX reported a little lower amount of silver, 0.2%. on the surface of the cell, which is point or spot number 12, there was also a bit of silver that EDX indicated. However, for point 13 and 14, 13 I didn't show here because its spectra was similar to 14. So 13 and 14 showed no any silver, although it seems somewhat whitish uh, on the image, but there was no any indication of the presence of silver. So these results suggest that there is interaction occurring with the bacterial cell surface as early as 10 minutes. It could be within few seconds, but we didn't do that, so we had a data only for 10 minutes, so we report as such. So the interaction may occur as quickly as possible. And these particles where we rather refer to it as a nanoparticulate instead of saying nanoparticle. So these were about 155 to 157 nanometer in diameter. So there is an indication that particles can grow as they come in contact with the biological surfaces. So here we are looking at the same E. coli cell under silver ion treatment at 10 ppm, and this is after 72 hours of exposure. So the cells look really nice. I'm not sure if our image, particularly this image, may make the cover of the journal, but perhaps after the paper is published, we may want to request the editor to see if they would be willing to do that. So again, looking at the bottom right panel, we are looking at silver. So this purple coloration is showing excess amount of silver ion on the surface. So silver ion, dissolved silver ion, was indicated to be present on the bacterial cell surface here that showed honeycomb-like structure. So this is really an interesting finding. So on this table, we are showing the magnitude of the charge. So this magnitude of the charge is shown as an absolute difference, meaning that we are not using the sign here or the direction of the sign. So we are using the absolute value. So E. coli alone minus 14 millivolts. So we are looking at zeta potential, and it is used as a measure to measure the interaction force. So we have day 0 minus 14.8 millivolt for E. coli alone in LB broth, and we have for day 3, which is 72 hour, and the E. coli charge slightly diminished and went to minus 10. For citrate silver nanoparticle, its initial zeta potential was minus 30 millivolt, and after day 3, well, on day 3 for E. coli, it was minus 15, and for amino silver nanoparticle, initial zeta potential was plus 41.6, that is the mean zeta potential, and the E. coli is minus 17. One may ask, why are these values for E. coli different? Each experiments were done individually or separately, so we included their own control. So these are E. coli control, but measured or followed until day 3. So there is slight difference, but if you look at initial E. coli zeta potential minus 14.8, and here after 3 days minus 15 or minus 17, so they are very, very close to each other, because zeta potential value is also not perfect as like the hydrodynamic diameter using the DLS. Now, looking at the charge difference or magnitude of charge difference, let's focus on amino silver nanoparticle. We have charge difference of 58.6. So the magnitude of this charge difference for amino silver nanoparticle is extremely high as compared to citrate silver nanoparticle. So this suggests higher electrostatic attraction between the high positive amino silver nanoparticle and the negative E. coli cell surface. So with that, we would expect higher toxicity, and the observed toxicity was also higher for amino silver nanoparticle and lower for citrate silver nanoparticle. So the main summary or takeaways from this research is that amino silver nanoparticle is bactericidal, while citrate silver nanoparticle is non-toxic, and silver ions are or where bacteria is static. So high positive charge amino silver nanoparticles had higher interaction with negatively charged E. coli surface, leading to higher toxicity. And we also found that amino silver nanoparticle treatment led to cell wall damage and adherent fimbriae inhibition. And these results are very significant as we are to control the hospital acquired infection or infection in general in the hospital clinical setting. So we have this paper, the second one, it's currently under review. It's a re-review. We resubmitted it after addressing the reviewer's comment. So the paper may be published anytime soon. And the third one is the what do you call preprint of the same paper. So there is slight variation in the title because our original title was near atomic size because it is 5 nanometer, which is almost close to the size of the atom. And one of the reviewers had a comment about why would you say near atomic size instead of saying what the size is. And then in the revision, we changed the title to 5 nanometer size. We also have a paper currently under revision. We received the reviewer comments and we are currently revising it, and hopefully by next week we'll be able to resubmit this. So this is the preclinical study on SARS-CoV-2 using a hamster model, and in this case we slightly modified our amino silver nanoparticle with additional ligand on the surface and tested tested against SARS-CoV-2, and our animal model was the hamster, golden Syrian hamster. The results are fantastic too. So once it is published, I would be happy to share with the group as well if there is an interest. Now I have a couple of more slides related with the bacterial study and our nanoparticle. So this is a study that my master's student or one of my master's student is currently undertaking, and I think I have a picture over here. So Jordan Williams is my master's student. She is continuing pursuing her master's in science in environmental health, and she's trying to graduate this spring. And our research interest is hospital-acquired infection and novel mitigation measures. So we are trying to use our amino silver nanoparticle and compare with antibiotics. And here we compare with two types of antibiotics, ampicillin and kanamycin, which are very common and widely used antibiotics. However, because of growing infection, growing antibiotic resistant, as well as multi-drug resistant organisms, there is a huge concern about the need. There is a huge concern about the infection that occurs in the hospital setting, and also the need for newer antibiotic or antimicrobial product. So several organisms belonging to gram-negative bacterial family like E. coli, Pseudomonas aeruginosa are some of the most resistant bacteria against the antibiotic. Bacilli, which is also bacteria, cocci, fungi. So these are some of the AR or MDROs. So looking at some of the stat, annually 1.7 million patients contract hospital-acquired infections throughout the United States. So that is a big number, and globally the mortality rate is around 10%, which is huge. Looking at the economic burden related with hospital-acquired infection, which is estimated to be around almost $10 billion annually. And I think this is little older data, maybe 2013 or 2018. So there is no, I think, most recent data. But hopefully in the next year or so, we'll have some data from the CDC. And central line associated bloodstream infection called CLABSI has been found to be the most costliest in terms of HAI. Patients admitted to ICU, intensive care unit, have a greater risk of developing these infections due to comorbidities, exposure to contaminated medical devices, declining immunities of the patients, and also increased antibiotic prescription or its use. Therefore, innovative antibacterial treatment modalities are needed to control ever-rising HAIs. So today I'm showing you the results of 20 ppm amino silver nanoparticle as well as antibiotic kanamycin, but we are also doing study at 10 ppm aminosilver nanoparticle, as well as kanamycin, and 40 ppm as well for both the compounds. We did that individually for individual compounds, and we also mix the nanoparticle with the antibiotic. I'm not showing the results for ampicillin, but we are doing ampicillin as well. So we are working on two bacterial strains, one E. coli and another Pseudomonas aeruginosa. Today I'm only showing you data on E. coli. The study on Pseudomonas aeruginosa is ongoing and it has not been completed yet. Again, the study, the bioassay is 48-hour bioassay, and for this bioassay we are using Diffusion test, or in other words, Kirby-Bauer diffusion test, which is shown in the figure over here. So here is a Dix, and the Dix will be soaked in the solution for a defined time period, and then you let the bacteria grow for 48 hours, and after 48 hours you would expect this halo to be formed. So presence of halo means that the test chemical is inhibitory against the bacteria. So these are the results. So what you can see here is, so the top right panels, on the topmost part we have 20 ppm kanamycin, and on the bottom panel we have the combination of kanamycin and aminosilver nanoparticle at 20 ppm each. So when you have an antibiotic alone at 20 ppm, which is kanamycin, the halos are there, but in some cases, nearly in half of the cases, you can see the halo is very faint and it's not well defined. Now, when it is combined with aminosilver nanoparticle, these halos are bigger and also very well defined. On the left side of the top panel, on the bottom, you see aminosilver nanoparticle alone. So in this case too, the halos are very clear and well defined, but little smaller than when combined with antibiotic. And on the top panel, we have control, no halo. That is what you would expect. Now with ampicillin, sorry, I think I mentioned earlier we don't have data for ampicillin, but yeah, we do have here. We have the plates, but we don't have the bar over here. So ampicillin did not show any halo, meaning that ampicillin is a very common, widely used antibiotic. It acts on the cell wall, so it destroys the cell wall. And kanamycin acts on the ribosome. I believe it is 30S ribosome. So when nanoparticle was combined with ampicillin, here there are smaller halo compared to nanoparticle alone, meaning that somehow ampicillin is blocking the efficacy of the nanoparticle, which is reflected here. But when it is kanamycin, actually they are working together, and perhaps there seems to be additive effect of these two chemicals. On the bottom, we are looking at the bar plot. So this is the bar plot, the tallest one, with kanamycin and aminosilver nanoparticle at 20 ppm each. And on the left side, we have silver nanoparticle, again 20 ppm aminosilver nanoparticle. So this bar aminosilver nanoparticle and this bar here with kanamycin, and as you compare the farthest bar here, the bar at the far right is taller, and perhaps significantly taller. We are yet to do the statistical analysis, so you are not seeing the bar here, but this could be significantly different from these individual compounds. So this suggests that there is a potential for additive effect with the combination of aminosilver nanoparticle and kanamycin at 20 ppm. Ampicillin was apparently non-toxic compared to kanamycin. So hopefully we will have similar results for Pseudomonas as well. Remember, Pseudomonas causes pneumonia and can also kill the patient. So Pseudomonas is again another strain. Sometimes we do see some or slight variation in the response of the organism different species of organism, in this case bacteria. But as once we complete the experiment, we'll be able to put together a manuscript and go for publication. So this is all I have for the first part of the presentation. So with that, I'd be happy to take some questions maybe for the next 5 or 10 minutes. You can leave the questions on the chat, or I really appreciate it if you can,
Yeah, participants, if you have any
yeah, ask the
specific
question
queries, you can.
orally. Yeah, there is one question here from Nathan. Being an antibiotic, why ampicillin didn't show toxic effect? Again, the big problem with hospital-acquired infection is that bacteria or fungi or viruses, they are actually becoming resistant uh, towards these common antibiotics. It could be because of their overuse. So somehow the antibiotics are losing their efficacy, and we do see it clearly. Couple of my students indicated that maybe antibiotic has gone bad, but we have been doing some testing looking at whether or not it is effective, and we did find that it is still active compound. So it is the bacteria that is developing resistance and therefore not responding to this antibiotic ampicillin in this case. Now, please feel free to ask questions. Okay, science is all about asking questions. We ask questions, and that's how we understand science better, and that's how we improve our communication as well.
Okay, actually, yesterday there was one query to me, Dr. Low. Actually, with respect to
Hmm.
that single particle ICP-MS. Okay, so
Right.
yeah, actually in India we didn't had, or when I did my research work, it was not available. So for to get it
Right.
access. So how is it possible? Is it available there in your institute, or did you had the chance of doing it, the single particle ICP-MS?
No, I have not. No, I have not had. I have not have a chance to do the single particle ICP-MS. But in my previous institution at Temple University,
Okay.
um, I think one of the professor in environmental health, she has single particle ICP-MS, and I think there are a couple of other labs in the U.S. That routinely do the single particle ICP-MS. So obviously we can approach them. There could be some cost involved if we are to run some samples.
Hmm. Okay. 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 I got your thing.
Thank you. We have another question here. Why there is significant zeta potential charge difference in amino silver nanoparticle and E. coli interaction? Yeah, so we are reporting the absolute value here. Yeah, so we are reporting the absolute value. So from plus 41, if you go down to 0, that is 41 as an absolute number. And if you go to minus 17, so you 41 plus minus 7 plus 17 would be 58. So the strength or the magnitude of that charge difference would be 58, and this is the absolute value. Okay, so you have the x-axis, right, or the line of origin, and you have plus 47, and you come to 0, that is 47, right, and you go down minus 17, so 47 plus 17, sorry, 41 plus 17, that is 58, right. So the total magnitude is 58. So that is how we calculated, and we did similar measurements in one of our previous studies, which is published. So we used that basis, and reviewers did not have any comment on the charge difference and the way we calculated the charge difference. So we are essentially doing a simple analysis based on Zeta potential, looking at the magnitude of the charge difference and um, inferring that, using that value to infer the strength of interaction. So you have high positive charge particle and you have negative charge bacterial surface. So there is a higher uh, electrostatic interaction, and that leads into particle coming in contact with the bacteria, which you also saw using the electron micrograph with 10 minutes of exposure, and leading to complete bacterial population collapse. Um, so cell wall damage is the major mechanism there, and we also did not see adherent fimbriae even at low concentration of 0.5. So our proposed mechanism of action is cell wall damage and adherent fimbriae inhibition. So even if you do one of these two, then you can address or mitigate the hospital-acquired infection related to bacteria in this case.
Yes, sir. My doubt was like uh, I, I understand how it is 58, but why this much difference is there compared to others?
So you're talking about minus 17 compared to minus 15 and minus 10.
Yes, sir. From plus 41, it came up to minus 17, right? So why this much? Is it representing the uh, magnitude of interaction?
Yes, I believe so. Yeah.
Okay. Yes, sir. In that case, did you check without E. coli, like only Ag nanoparticles after 3 days, like without E. coli?
Yes. Right. Yeah. We did check that, and not only 3 days. We have almost same Zeta potential value for just the nanoparticle, right? For over 3 years, right? And it stays very close to that 40 value.
Okay, sir.
So it's a highly stable suspension.
Okay, sir. Yes, thank you. And one
Yes.
more notice, I have seen in that EDS spectra, other elements are also present. So why is that so? Like silica, aluminum.
Yeah, silica, you can expect silica on the stop that we use. So the signal of silica is coming from the stop.
Okay, sir. Okay.
And silica is also common. I think the microscope may also have silica from previous samples, and the water or the broth may also have some silica. So silica, oxygen, carbon, oxygen, these are biological molecules,
Yes,
and
sir.
you'll always find those in the biological samples, right? And we have
Yes, sir.
phosphorus, that is also very common in the biological sample.
Yeah,
Yeah.
I
And
understand
sodium,
these things. Yeah, but from where those silica, aluminum came, that's what.
yeah, aluminum is definitely from the stop because it was made of aluminum, right?
Okay, sir. Okay.
Yeah, oxygen, potassium, chloride and sodium, they are in the water. Uh, so, and they are also in the biological materials, I would say.
Yes, sir. Thank you.
You're welcome. If there are no other questions, I think we can take a short break, maybe 5 minutes, and then we can come back again.
Yeah, we can have a break for 10 minutes as well, Professor Lou.
Okay, yeah,
Or
we can do
for
that.
yeah, and then we can start. Otherwise, we can take 5 minutes, and then for the next session we can have 10 minutes, or we can wind it up early also, because as you are there in the midnight, so so
It's okay. It's the last day, so It doesn't
Okay,
matter.
okay.
Yeah.
So
All
yeah,
right. Yeah. Let's do
okay.
5 minute break and then we'll come back. Okay.
Yeah. We can start by 9:55 or 56. Yeah.
Awesome. Thank you so much.
Yeah, look, so look, we can start, I feel. Yeah.
Sure, sure, yeah. All right. Welcome back, everyone. So, this is our last lecture for the week. Uh, so, in this lecture, lecture 8, I'll be talking to you about understanding risk assessment process, how the conventional risk assessment process works, and some of the limitations of using this method for engineered nanomaterials or engineered nanoparticles. Um, so, as I mentioned earlier, so I'll be talking to you about different steps involved in risk assessment process as used by the US EPA and originally published by the National Academy of Sciences of the United States. And then at the end, we'll talk about the limitations of using this framework for the risk assessment of engineered nanomaterials. So before we get into the process of risk assessment, I think it is important to understand the major actors of risk assessment in the United States. Um, the primary actor is the United States Environmental Protection Agency, US EPA. US EPA is charged to keep our environment safe as well as to protect public health. Next is Agency for Toxic Substances and Disease Registry, Atsdr, which is a part of CDC. National Research Council of the National Academy of Sciences originally published this paradigm, and then US EPA started using it, adopted it. We also have OSHA, which is Occupational Health and Safety Administration. So OSHA is charged with keeping the employee safe in the workplace environment from the chemicals or the hazards. And we have NIOSH, which is National Institute for Occupational Safety and Health. NIOSH actually develops threshold values or the standards for different contaminants, and OSHA implements them. So the process of risk analysis. There is a difference between risk analysis and risk assessment. Risk assessment is a part or a component of risk analysis. Risk analysis is more a broader term, and within risk analysis we have risk assessment, risk management, as well as risk communication. So risk analysis involves a review of scientific studies. Almost in any case, you have to study what the science is. Because of internet or access to internet today, more so than I was in graduate school in Nepal, we just relied on one textbook at the time. But today, all information is on our fingertips. We have to review the scientific studies or the papers, as well as reports from the government agencies or private agencies, especially the credible ones. An understanding of the properties of risk is essential when you are doing risk analysis. An assessment of levels of human exposure and dose. So you have to have an understanding of the human exposure, the degree of human exposure, and the dose that humans might be exposed to. And then finally, at the end of risk analysis, or I would say risk assessment process, you'll come up with some concluding statements. Your concluding statements must include the likelihood of risks happening, occurring, the impact of the risks, the impact of the hazard in question, and the extent of the risks, which is the magnitude of the risks. So all of these aspects must be clearly written in a plain and simple text when you are concluding your risk assessment. And risk assessment is a part of risk analysis. Risk analysis uses components of various disciplines. So, as we learned before with ecotoxicology or ecotox, we said it is a borrowed science. In this case, with risk analysis or risk assessment, you have to have information or some level of expertise on various branches of science. And more importantly, chemistry, toxicology, epidemiology, medical studies or medical science, as well as some kind of measurements. If the toxicants or the contaminants are in the environment, then it will be environmental measurement. But these are all analytical measurements. So you have to have some values, some numbers to work with. So some of the tools of risk analysis. So these are the different sciences, and I'm not going to discuss about all of these sciences because we already know those sciences. But toxicology is very important and is directly related with risks. So briefly, I'll touch on toxicology. So toxicologists like us study chemicals to determine their physiological and health impacts on humans. Regulatory toxicology aims at guarding the public from dangerous chemical exposure. So regulatory toxicology may look a little different compared to general toxicology. The most of the papers you see on nanotoxicology, people will be measuring a couple of endpoints here and there. They may have just two concentration, and in our case also some examples you saw two concentration being used, because our interest was not to develop a dose or full-blown dose response curve or identify EC50 or LC50 or EC10, LC10, and the like. So those kinds of parameters or those kinds of values are more related to regulatory toxicology, because when you make regulatory decisions, you have to have those key points or key endpoints to make a informed decision. So some of the endpoints with regard to toxicology is NOEL, NOEL, or NOAEL. So these are more or less synonyms. NOEL stands for non-observable effect level or no observed effect level. NOAEL, NOEL, stands for no observed adverse effect level or non-observable adverse effect level, and LOEL stands for low observable or lowest observable adverse effect level. So these are some of the endpoints at the lower end of the toxicity. When it is no observed, that means no any adverse effects are observed at that higher concentration. And when you say low observed or lowest observed, so that is the lowest concentration where measurable toxicity is observed. Excuse me. And lower value is or can be slightly higher than null value. And this indicates some kind of potency of any toxicant. As I've been talking about National Academy of Sciences, so National Academy of Sciences published a guiding document in 1983 called Risk Assessment in the Federal Government, Managing the Process. So managing the risks of the chemical contaminants in the environment. In the US, in the past, there used to be a lot of landfills and hazardous waste sites. So, so there was problem in managing those sites, and that actually prompted, or that was one of the reasons that prompted NAS to come up with some guiding document which allows the regulators to assess the risks in a more consistent way, so that it is comparable regardless of when it is done and who does it. Excuse me. So the NAS paradigm of risk assessment 1983 involves four major steps. First being hazard identification. The second one is dose response assessment. The third one is exposure assessment. And the fourth one is risk characterization. If you look at some of the risk paper, you might see second step and third step interchange. What that suggests is you can understand the background of the authors, which means they may not know about the NAS paradigm, the original concept, right? So they may just flip it between dose response being the second step is moved to third step, and exposure assessment is moved to second step. There is nothing wrong in doing so, but that will indicate, at least for the technical risk assessor, that the person or the individual or the scientist may not know about the real background of risk assessment. So the first step, hazard identification, involves identifying a chemical or chemicals that present a risk to human health. So whenever there is a leakage, or there is a spill, or there is a hazardous waste site, there is a landfill or an old abandoned landfill, we need to assess what chemical might be present or how many chemicals might be present. If there is one chemical, life will be much easier to assess, but if there are multiple chemicals, it takes more resources and time to assess. First, to identify the chemical, and then to assess the risk. So this step also involves performing a qualitative assessment of a chemical potential for negative health impacts on humans. So after you identify a chemical or chemicals in a given site, you need to understand the toxicity profile of that chemical. So it could be a qualitative study. If you are just doing literature review on that particular chemical, so Atsdr, which is a part of CDC, they publish toxicity profile of several chemicals. So the first thing a risk assessor would do is they would go to the Atsdr website, atsdr.gov, and then look for toxicity profile for that chemical. And usually these profiles document a very long document, several hundred pages long, and it will have almost every detail that you need to know about that particular chemical. So that is a qualitative assessment. Literature may already be present. All you need to know is you need to go back and look at the information toxicity profile of that chemical. So this step, first step, hazard identification, entails the qualitative analysis as well. Identifying could be quantitative because you have to measure the compound. You have to identify the compound. So if it is the metal, you will run the ICP-MS and you can detect the compound, or AAS. If it is organic compound or organic contaminant, perhaps you may do a GCMS or HPLC, depending on the sensitivity of the instrument and the type of the chemical. And sometimes there could be unknown chemical, and it may take a while to determine those chemicals. For nanomaterials, again there is limitations, but you can at least identify the chemical makeup of the compound. Second step in risk assessment, as done by the US EPA according to the NEST paradigm, is the dose response assessment. So dose response assessment provides a quantitative view of the risk. So you are looking at the dose and you are looking at the response for that particular chemical or for that particular hazard. So this step also involves a review of scientific studies and data, so which is qualitative. In this case, the magnitude of response is correlated with dose. So this is just a general statement. It doesn't always show a direct response based on the dose, but in general, in toxicology, we say that the magnitude of a response is correlated with the dose. So these are some basic dose response curve, as you will find in the literature or any toxicology textbook. The first one, top left, is the S-shaped growth curve or the sigmoid growth curve. Most of the metals or toxic compounds may show S-shaped growth curve. Sorry, it's not growth curve. I apologize for that. So dose response curve. On the right, top right, we are looking at U-shaped dose response curve. Although it looks like a V, it is called U-shaped dose response curve. And U-shaped dose response curve is really important because the shaded portion here that you see is called the region of homeostasis. Those elements which are needed for the body, for the normal functioning of the body, for maintaining the normal homeostasis, those elements are required at certain dose. So there is a lower threshold here and there is a higher threshold here. So below the lower threshold, if you have that element lower than this value, it leads into toxic effects. If you have the same element higher than this value, it also leads into toxic effect. And if the value is so small or so large, then it may also result into death. So many micronutrients, vitamins, they tend to show U-shaped dose response curve. Now the bottom plot or the dose response curve is called linear dose response curve. It is also called linear no threshold model. So it is called no threshold because this is a line that begins at the origin, right? And it goes straight diagonally. So meaning that any value above zero might be toxic. And this is a classical dose response curve that is used to represent radiation toxicity, right? Which is the I would say, physical hazard. However, this model has been contested, suggesting that this model may not be really true because there are evidence from many parts of the world where the background level of radiation is higher than other places, and even if the background level is higher, the cancer rate in the inhabitants or people living in those areas is not significantly higher, suggesting that the body may have some protective mechanism against low dose radiation, and therefore this linear, very straight line, linear dose response curve may not be a true curve. But this is a classical example, and this is the slide, this is the graph that we must show our students when we are teaching toxicology or X. This is a simple schematic. We are looking at effects of amount or a dose on response, right? Uh, Imagine these cups are humans, right? So they are same size humans, same body mass, but we are looking at different dose, right? When you have the body mass same and you increase the dose, obviously you will see a higher response with higher dose, and that is very classical understanding. So toxic response is directly proportional to dose, and when the body mass is kept constant. Now here we change the body mass and we kept the dose constant. You have the same dose, but if you have a different body mass, imagine that big cup is the adult body mass and the small cup is the child body mass. So even you are exposed to the same amount of a toxicant or a contaminant, the response would be different. So the dose is eliciting perhaps no response or little response in adult, whereas in child the dose is seems to be highly toxic, indicated by red color. Now the third step in risk assessment is the exposure assessment. So the purpose of exposure assessment is to measure or quantify a person's exposure level. How much is a person exposed to a given contaminant or a given hazard or hazards? If there are multiple hazards that were identified in step one, then you'll have to do the exposure assessment for all those hazards. So it is important to note that exposure or exposure concentration is different from dose. So exposure refers to what is in the environment, right? The amount that is in the environment that we are exposed to. Dose refers to what is actually taken in by the body, okay, or by an organism. So what goes inside the body, how much goes inside the body, that is a dose, and what is in the environment that we are exposed to is the exposure concentration. So we must understand the difference between exposure and dose, which is very important. Dose can be influenced by many factors, such as how the substance enters the body, whether absorbed through skin, the absorption coefficient, or the rate of absorption through the skin, rate of absorption through the GI tract, or through the respiratory tract or respiratory system, are altogether different. So, depending on the route of exposure, right, which part of the body is exposed, the dose that enters the body may differ or will differ. The fourth step in the risk assessment process is called risk characterization. So, in this stage, the fourth stage, which is also the final stage of risk assessment, is where you come up with a magic number, the final number that you come up with after performing the risk assessment. Uh, Gives an estimate of the severity of the risk from that particular hazard or hazards, the likelihood of the risk that may occur, which is probability. When you're talking about likelihood, we are talking about probability of something happening, and generally the probability ranges from 0 to 100%. And the consequences of that hazard. Okay, what are the endpoints? What are the toxicity endpoints? That is the consequences. The risk characterization includes an estimate of the negative effects to expose individual for a given contaminant or a hazard. Now, finally, at the end of risk characterization, it is important that we provide a concluding statement. And generally, typically, the concluding statement for risk looks something like this. It could be deaths per million people in a select population or selected population or in a nation. It could be in a small town too. Deaths per million people within a certain radius of the released pollutant. Deaths per weight in tons per pound of the toxic substance or substances released. Or in some cases, you'll also find people using loss of life expectancy associated with exposure to the toxic materials. So often, real risk assessor generally do not use the statement like you saw, the fourth statement here, the last statement. And usually people with epi background, epidemiology background tend to use statements like the last statement, statement number 4. So let's dig a little more deeper into risk characterization, which is the most important part of risk assessment process. Because after this stage, upon completion of this stage, you'll come up with the magic number, and that magic number is very, very important. It is important in the sense that it will tell you what the risk is, right? What the endpoint of the risk is, and how you may want to manage the risk. Risk mitigation is very important, because just knowing the risk is not too important. Knowing the risk and then managing the risk is critical, because the intent here is to protect the public health from exposure and toxicity of that particular compound or of that particular toxicant. So a risk characterization cannot be considered complete unless the numerical expression of risks are accompanied by explanatory text interpreting and qualifying the results. What this means is you have to have a concluding statement explaining that risk value that you come up with at the end of the risk characterization process. This process can be further subdivided into 6 processes or 6 steps. Okay, step 1, step 2, 3, step 6. Step 1 involves review outputs from toxicity and exposure assessment. So you need to look at toxicity data, exposure data, very detailed. Okay, and sometimes it takes several years to review these results or the data related to the hazards. Then step 2 involves quantifying risks from individual chemical. For each individual chemical, you have to quantify risks. Step 3, quantify risks from multiple chemical. And you can combine those risks for multiple chemicals. Step 4, combine risks across exposure pathway. You can also combine risks across different pathway. Risks from the soil exposure, risks from water exposure, risks from air exposure, risks from sediment exposure, risks from biota exposure or food exposure. And then step 5 involves assess and present uncertainty. So what is the uncertainty in the data? When it comes to nanomaterial or engineered nanoparticles, it's all about uncertainty. And uncertainty is so huge that we cannot perform a risk assessment. Step 6, consider site-specific human studies. So if there are multiple sites, then each individual site must be studied separately. So step 1 Review outputs from toxicity and exposure assessment. When you do science, obviously, as you know, science is the systematic study of anything, right? So here also you have to organize the output, organize the data in a meaningful way, uh, if possible in a standard way as used by the EPA as suggested in the NAS document. Okay. Otherwise, you can organize data in your own way as well, as long as it makes sense. Exposure duration, organize outputs for exposure duration. Absorption adjustment, if there is a need for adjustment for the absorption, you have to do that. And I think I do have a couple of slides showing the adjustment. And then consistency check. Consistency check is nothing. It is just that you have to constantly monitor what you are doing. You have to constantly look at the literature. You have to constantly review the literature of all kinds, so you don't leave any information that might be helpful in making or in changing the conclusion. For some reason, it seems like my slides formatting has been obscured. So here we are looking at necessary exposure information. Estimate intake. Intake. How is the intake occurring? Is it through the skin? Is it through the respiratory system? Is it through the GI tract? So you need to estimate those intakes, whether it is one route of exposure or whether it is multiple route of exposure. You need to understand that and then estimate the intake. Exposure modeling assumptions. So sometimes intake value may not be available for a given compound, right? But there could be some modeling results available in the literature, or you can also model results based on the literature value. So you can borrow the literature value and then model the exposure using some kind of statistical modeling. List of corresponding exposure pathways. So you need to know how many exposure pathways are available, whether it is soil, whether it is water, whether it is air. So these are three primary route of exposure. Sometimes it could also be food or the sediment. Adjustment from administered to absorbed dose. So you have the administered dose. Administered dose could also be taken as the exposure concentration, as I mentioned earlier, meaning that the concentration that is present in the environment. Okay, that is the administered dose, because you come in contact with the environment and it gets administered, and as it gets administered, not 100% gets administered most often. So there is certain fraction that gets administered compared to what was in the environment or what is in the environment. So there has to be some kind of adjustment being conducted. In the absence of any information on absorption, assume an oral absorption. So if you don't have information about the information about the absorption or route of absorption, then you can use oral absorption as a default route of absorption or route of exposure. You can obtain assumption from information for related chemicals. If you don't have absorption information for your chemical X, then perhaps you may have information about similar chemical in the literature, which you can use. Assuming 100% would be non-conservative approach. It's not a good idea to assume 100% goes into the body compared to what is in the environment. A conservative assumption would be 5% absorption, but 5% may not be true, right, for all chemicals. So you cannot just use 5% or 100%. Both may not be correct. Knowing what actually is the rate of absorption based on the literature, if you use those values, your final risk characterization would be more meaningful. Now, adjusting RFD. RFD stands for reference dose. In other words, or simply speaking, it is the safer dose. It is the maximum dose at which there is no risk when you are exposed to that chemical for a lifetime. When you say lifetime, we are talking about 70 years of exposure duration. Okay, that is a default value used by the EPA and recommended by NAS. So one example here for oral RFD, oral reference dose, is 10 milligram of chemical X per kg body weight per day. Now, from the literature, we found that that chemical X absorption efficiency through oral intake is only 20%. So 20% of 10 is actually 2 milligram per kg per day. So this is how, using a simple math, you can adjust the RFD value. Here we are adjusting ingested dose to absorbed dose. So what amount gets absorbed from what was intaken or ingested. For example, ingested dose is 40 milligram of chemical X per kg body weight per day. And from the literature, we learned that human oral absorption efficacy or efficiency is only 10%. So 10% of 40 is 4. So you use the adjusted absorbed dose for your risk characterization purposes. Now step 2 would be quantify risks from individual chemical. So if you have multiple chemicals, you have to quantify risks for multiple chemicals. Risks from carcinogenic effects. So this is for cancer risks, okay? Two kinds of equations have been prescribed or recommended in the NAS document. The first, the most common one is risk equals CDI. CDI stands for chronic daily intake. And we're talking about cancer, and cancer is generally expected to have long incubation period. So we are estimating chronic daily intake, which is a measure of chronic exposure for that chemical. So CDI times SF. SF is the slope factor. Slope factor is also called cancer potency factor. And cancer potency factor or slope factor are available in the literature, so you can simply use the literature value. Now this risk equation, risk equals CDI times SF, is generally used for the low risk condition. And what that means is if your final risk value is below 0.01, 0.01 means 1%, 1% means 1 in 100, right? So what that means is if 100 people are exposed to that chemical X, then you expect 1% out of those 100 people or 100 population size of 100 to develop cancer if they were exposed to that chemical X for 70 years, which is the lifetime. So if your risk value, final risk value, okay, is below 0.01, then you use this equation. Otherwise, you use the second equation or the bottom equation, which is risk equals 1 minus exponent to negative CDI times slope factor. So this equation is generally preferred when there is higher risk, higher than 1% risk, in which case you have to use the second equation. So this is another example. We are looking at private well, okay, private drinking water well. In the US, I believe about 1/3 of the population rely on private wells for drinking water purposes, because many folks do not believe on government water, okay, the tap water. So they tend to use their own water. The problem with that is if you don't test your water or your private well water, there could be a lot of contaminants coming from the surface or subsurface, such as benzene could be present in the groundwater, and therefore it could be in a private well too. And exposure to benzene can cause cancer. Benzene is a known carcinogen. So the concentration of benzene, CW, that is concentration in water, okay, is 7.5 microgram per liter. So this is just a hypothetical value. I'm giving an example. Benzene is a class A carcinogen, which means it is a known carcinogen with a slope factor of 0.029, reciprocal of milligram per kg per day. So this slope factor value we got from the literature, okay. If you don't have the slope factor, you cannot calculate the risk for the cancerous agent, okay, or carcinogen. In which case, what you can also do is you can borrow the slope factor from a related compound and calculate the risk. So with that, so here we are looking at how to calculate CDI. So CDI is a measure of exposure, okay, but we need CDI to calculate risk. Now going back, you look at the risk equation here. So there is CDI here, and there is also CDI here. So you must calculate CDI first and then multiply with slope factor. Then you work out the equation. Then you get the risk, okay, whether it is low risk or high risk. So CDI is a measure of exposure. So now here we are calculating CDI, chronic daily intake. So again, the equation or the formula is very simple. So we have CW. CW is concentration in water. IR is ingestion rate of that particular chemical, in this case benzene, from drinking water. EF is exposure frequency, and ED is exposure duration. Exposure duration is 70 years. Okay, for anything that is potential carcinogen, you take the lifetime exposure, which is 70 years of exposure. And EF is exposure frequency. What that means is how many days in a year you are exposed to that contaminant. If you are exposed in the occupational setting, perhaps it will not be 365 days, right? But if you are exposed at your home, it will be 365 days of exposure. That means throughout the year you are exposed. So that is EF, 365 days, and ED is exposure duration, which is 70 years. BW is body weight, and AT is averaging time. Averaging time, EPA uses averaging time. Averaging time is nothing. It is just the product of EF and ED. Essentially, EF and ED and AT can cancel out, so you can actually remove those as well to simplify the equation. Now, this is again another example for calculating cancer risk. We have concentration in water for benzene at this milligram per liter. If you are given microgram, it is important that you change the microgram value into milligram right away. Otherwise, later it leads into confusion. Ingestion rate, 2 liters of water per day. That is a typical water ingestion rate expected by an adult. But if you are an army personnel working in the desert, perhaps your intake rate would be maybe twice the normal average intake rate for water. And in which case, if you drink more water, obviously there is dilution. But if the concentration of the chemical is high enough, then with more water, you have more chemical in the body. And carcinogens tend to bioaccumulate in the body. They are lipophilic as well. And perhaps your exposure is going to be higher, and therefore your final risk could be higher. Exposure frequency, 365 days. Exposure duration, 70 years. So we are looking at lifetime exposure. Body weight, 70 kilograms. So this is the default body weight used by the EPA. You can use specific body weight also if you want to. And averaging time is again exposure frequency times exposure duration, 365 times 70 years. So this is simple math. Anybody can calculate fairly easily. So again, those values are plotted here. Yeah. And finally, as you work out this problem, the CDI value is seems to be somewhere over here. Use that CDI value, multiply with SF. SF value comes from the literature. Then you get the unitless quantity, and that will be your final risk value. 6 times 10 to the power minus 6. So what that means is 10 to the power minus 6 is the reciprocal of 1 million, right? So you have 6 in a million, okay? So out of 1 million people, you have 6 excess cancer rate. If your exposure CDI exposure concentration is this much of benzene from drinking water, being exposed over a lifetime, 70 years, for a 70 kg adult human being who drinks 2 liters of water per day. Okay. So this is the final concluding statement. I already mentioned it. You must always have a concluding statement written in very simple and plain English, something like this. And this is a very typical statement. 6 in a million people. So out of 1 million people who are exposed to benzene at that concentration, CDI, okay, there is a probability of 6 people, or you can say 6 excess people, developing cancer when they are exposed to that level of benzene over a lifetime from drinking contaminated water. So if you calculate and then provide a statement, so that will be a complete risk assessment, okay, and that is what is expected. And remember, my heading is missing here. So here it is low risk. So this calculation is for low risk environment. Why is it low risk? Because this is 6 in a million. 1% is 1 in 100, right? 6 in a million is very small quantity. 1 in 100 is very large quantity. Out of 100 people, one person getting cancer versus out of 1 million people, 6 people getting cancer, right? So this is a lower value compared to 0.01, okay, which is 1%. So this is a low risk calculation for benzene from drinking water. This is just a table to show you how you could use a table to represent to communicate the risk value. Uh, so here you have different pathway. I think something is missing here on the second row. There should be water here, and here we have fish. Okay, so with water, so the contaminant here is chlorine. CDI is this much through that pathway. Okay, slope factor is 1.3. Chemical specific risk through the water pathway is 2 times 10 to minus 4. So 10 to minus 4 is 10,000. Okay, so out of 10,000 people who are exposed to chlorine through water, 2 people may get cancer. Okay, out of 10,000. Total pathway risk, since there is only one pathway in this row, is the same like here. In the next row, you have fish. Okay, the concentration or the exposure is lower than what you saw from water, directly drinking water. And the risk here from fish is 1 excess risk out of 10,000 people who are exposed to chlorine through consumption of fish. So again, the total pathway risk for fish consumption is again the same as it is here in the previous column. Now, total exposure risk in the final column is the summation or addition of the risks from water as well as risks from fish. So out of 10,000, right? 10,000, 10,000, you can have it common, and 2 plus 1 would be 3. So it is a simple summation or addition of these risks. Okay. So this is how you will be presenting a risk value, in this case the cancer risk value, using the standard headings. And this is preferred by the EPA and obviously recommended by the National Academy of Sciences. So that was cancer risk calculation. Okay, and there is so much to learn about risk assessment. I teach risk assessment at the doctoral level for our DRPH public health students, and it is a full semester course, right? So it is a 15-week course, and I'm trying to cram this in an hour or so. So you can imagine there is a lot of information missing. Okay. However, if anybody is interested to learn more about it in the future or have any questions, okay, obviously at the end of this presentation we'll have some questions. But in the future too, as you're undertaking the risk assessment, you have questions, you need some guidance, feel free to reach out. Okay. So hazard index is the term that we use for non-carcinogen. So broadly speaking, under risk assessment, you either have cancer or you have non-cancer. Okay, everything that is not cancer is a non-carcinogen, and all the diseases that are not cancer are lumped under hazard index. Okay, HI. So hazard index is calculated separately for chronic, subchronic, and shorter duration exposure. So chronic is above, generally considered above 7 years. Subchronic is anywhere from 2 weeks to 7 years. Okay, and shorter duration exposure could be lower than 2 weeks, and it is calculated separately for each of these exposure duration. So hazard index is the sum of more than one hazard quotient for multiple substances and or multiple exposure pathways. So you should quantify hazard quotient individually for individual compounds, individual pathway, individual route of exposure, and so on. And finally, as you combine the hazard quotient HQ for multiple route of exposure, multiple pathways, multiple compounds or contaminants, as you combine them together, so this is sigma, which is the summation, that is addition, then that is called hazard index. So hazard index is the sum of all hazard quotient or HQ. You can also say HQs. So To calculate individual HQ, you need exposure concentration. Okay, you need the exposure. What is the exposure value, right? Which is actually here CDI. In some literature, you'll also find ADD. ADD is average daily dose. Okay, here it is CDI, chronic daily intake. So it can also be replaced with average daily dose ADD. So you have exposure concentration. You divide that by RFD. RFD is the safe dose. In other words, you can also call it benchmark dose. Excuse me. So the simple ratio of CDI and RFD will give you HQ, and if you have multiple HQs, combine them together, that will be a hazard index. So this is a table that the EPA recommends that we use as a risk assessor, and this is for a non-carcinogen. So you see here hazard quotient, and here we have PHI is pathway specific hazard index, and THI is total hazard index. Okay, for individual pathway, that is pathway specific hazard index, and for total hazard index, you combine this pathway specific hazard index, you get the total hazard index. So 0.4 and 0.2 gives you 0.6. So these are different pathway, well water, and we have fish here. Okay. Now the fifth step within the risk characterization, which is the fourth step of risk assessment. Risk assessment, right? The major process. Within risk assessment, we have risk characterization, which is the fourth step. And within the risk characterization, the fifth step is assess and present uncertainty. Remember, when we do any science, there is always uncertainty involved. And this uncertainty is basically coming from two different things. One, variability in data, and two is uncertainty itself. Okay, so uncertainty involves uncertainty and variability. So variability is true heterogeneity or diversity between individuals. There is always individual to individual differences. Diversity between species, right, of different kinds, or differences or heterogeneity among the samples. Even within your replicates, for environmental samples generally, or typically we use 3 replicates, but more replicates you have, the better data you have, right? So there is always going to be some level of heterogeneity. So that is what we call variability. Okay, and uncertainty by itself originates from the lack of knowledge, right? Something we don't know, or methods limitations. Many instrumentations, they have limit of detection, right? You have limit of detection, which is actually the lowest limit, right, that you can reliably quantify. And sometimes, in some cases, if you oversaturated that instrument sensor, it may not detect. It could give you erroneous result. So there are methods limitations as well. And when it comes to nanomaterials, here I give an example. There are a lot of limitations. Okay, so which means there is a lot of uncertainty related with engineered nanomaterials. And this uncertainty comes from not only the lack of instrumentations or proper instrumentations, but also lack of knowledge. What makes them toxic, right? We are not clear yet. Where do they go in the body? Where do they reside? Where do they accumulate? We don't have that information. What makes them accumulate in certain part of the body? We don't have that information. We don't have pharmacokinetics and pharmacodynamics data for these nanomaterials, right? So if you don't have those toxicity data, if you don't have the dose response data, you cannot perform risk assessment. Okay, so all those information related to toxicity, related to exposure, exposure is related to quantification of exposure, right? So a lot of uncertainty exists in the nanomaterial data, and therefore the foundational concept of risk assessment as presented here, as used by the US EPA. CDC also uses similar method, but they have 6 steps instead of 4 steps. But all those 6 steps, if you combine together, it makes 4 steps of the US EPA concept. Okay, So essentially, it's the same process. But CDC generally relies on more qualitative information. Um, so they generally tend to do preliminary investigation, and then if their preliminary investigation seems to show some risks, then they will refer to EPA, and EPA will come and do more detailed analysis, including the lab work. Now, what is acceptable risk? Remember, we as a mankind, we tend to accept certain level of risk. Living in a certain area, you have to accept certain level of risk. If you live in the beach area, uh, your perception of hurricane and the response to hurricane may be different than if you live far inland, right? So depending on the area, depending on education, depending on gender, and depending on the upbringing, depending on the peer, our friends, right? Uh, the perception of the risks varies from individual to individual. Even within the same family, between the individuals, among the individuals, among the family members, the perception of risk varies. EPA has come up with some numbers. Okay, so EPA considers these levels of risk acceptable, and if a risk value comes within this range, EPA will not do remediation or mitigation for that particular chemical for that particular site. Okay, so for cancer, it is 1 in 10,000 to 1 in million. So if you have cancer risks in this range, 1 in 10,000 to 1 in a million, excess lifetime cancer risk, that means it is an acceptable risk, and therefore not even a single dime will be invested to mitigate that risk. Okay, so non-carcinogen for non-cancer causing agent, hazard index, the sum of all hazard quotient, if it comes to be lower than 1, there is no risk, it is an acceptable risk. Okay, so further action will not be taken in terms of remediation mitigation of that hazard or the risk. If the hazard index is 0.99, that means it is below 1, so no action will be taken. True risk is between 0 and worst case scenario. So the true risk lies between 0 and worst case scenario. In this case, worst case scenario would be 1. Okay, the probability for 1 equates to 100%. So between 0% to 100%, or 0 and 1, is where the true risk lies. Step number 6, consider site-specific human studies. Always try to find human studies or human data, but it may not always be possible. Okay, but you should try looking for it. You have to summarize the data needs for a specific site, land use pattern, past land use pattern, present land use pattern, future land use pattern is also. Contaminant levels in the media, you have to quantify that, and that is done in the exposure assessment section. Environmental characteristics affecting freight and transport. So freight and transport are other factors that may affect the exposure, and I think Dr. Brajesh Dubey talked to you about freight and transport in more detail in his presentation. Potentially affected population. So what age group, who are affected, right? It is important to know, because today we know that different race, different gender, and different ethnicity have different sensitivity to different chemicals. Potentially affected biota. So if you're thinking from the environmental standpoint, you have to look for biota, plants and animals. What plants and animals are also affected? Are they related to human health? Do humans consume them, right, directly or indirectly? So you have to do some level of assessment in that regard as well. So that is all about risk assessment that I wanted to talk with you today. Now, on this last slide, I believe this is the last slide. Yes. On this last slide, we have just a summary of the challenges that we face as a scientist in terms of risk assessment of engineered nanomaterial or engineered nanoparticle. So again, I'm not going to read this all, but as you can see, there are several aspects that we need to characterize. And for engineered nanomaterial, I think almost for all of these aspects or entities, we lack information, and therefore credible risk assessment cannot be performed. Uh, if you perform risk assessment, people may laugh because there is a lot of uncertainties. There is a lot of uncertainties related to availability of data and the knowledge or the science of engineered nanomaterial. So with that, I think we have about 8 minutes or so. I would be happy to take questions. And again, as I said, in the future, if you have anything going on, you need some guidance on nanomaterial toxicity, nanomaterial experimental design, characterization. We have DLS as well in our lab. We also have electron microscopy in the university. So any assistance, if you need, please feel free to reach out. Okay, so I've listed my email address here, and obviously you can also Google me. So with that, I'll be happy to take questions that you might have.
Yeah, participants, if you have any questions or suggestions or clarifications on any doubts that you have, how to proceed, and then you can just interact with Professor Lin.
Absolutely, yeah. Any suggestions, comments, are welcome too.
Thank you so much, sir. It was a wonderful lecture all the week. I'd like to, like, sir, my area of research is microplastics. So I'd like to ask a few questions. Like, when we have, when I would like to perform any LCA study or a kind of thing with respect to microplastics. So how,
Right.
when the data is very less and it's like difficult to collect the data from the industry or from outside. So in that case, how we will be like approaching to proceed further with the existing data or available data.
So the question is, should we just use available data and do the LCA, right?
Yes, sir. Yes, sir.
Yeah, I think that is acceptable. Um, but frankly speaking, I have not done the LCA. I think Dr. Dubey might be able to help directly because he has done a lot of LCA, uh, life cycle analysis for contaminants, for waste products or waste materials. Uh, but yeah, I think you can run with the available data, whatever you have, uh, with the life cycle analysis. Life cycle analysis is different from risk analysis. Risk analysis, or risk characterization, or risk assessment is a regulatory framework, right? So it is mandated by law for the agencies like US EPA and CDC to conduct risks of given chemical or chemicals to protect public health. So it has regulatory implications, and it must be done in a certain way. Otherwise, there will be lawsuit filed um, against the agency if it is not conducted in a proper fashion. And therefore, they tend to stick to the framework. So the data or the risk results can be compared over time.
Okay, sir. Thank you, sir.
You're welcome.
Any other questions?
Seems like there are no other questions. Any comments, suggestion?
Sir, I'd like to ask one more question.
Sure,
Sir,
absolutely.
when the microplastics were present in the wastewater or any water stream, so like what is the best way to characterize the risk, like what the like characteristics on the characteristics of the water? For example, if it is wastewater, how the microplastics duration or its existence in wastewater affects the COD, BOD like parameters.
how the presence of microplastic affect the water quality parameters?
Yes, sir. Yes.
Yeah, that's a really good question. So what I would say is perhaps running the control sample without microplastic and comparing with the sample with the microplastic might give you some information. I think perhaps before even you do that, you need to first confirm whether or not the sample has microplastic, right? And I think one way to confirm would be doing the imaging for the water. So electron microscopy might be able to show you the microplastic morphology, and also if the electron microscopy has EDAX sensor or a probe, it will be able to characterize the elemental composition of the microplastic. Although it is plastic, it might uh, be carrying some of the metals or other compounds on the surface, so which may play some role. I've not looked very deeply into the microplastic literature because our focus is not microplastic, at least um, in the interim, right? But I think those are some of the things that can be done to ascertain the potential influence of microplastic uh, in the wastewater quality or for the wastewater quality.
Yes, sir. Thank you.
You're welcome.
Yeah, I think there are no questions, I feel, Professor Loh. So, in that sense, I would take this opportunity to thank you for sparing your time, be it the early hours or otherwise the late nights, for the participants, and then on behalf of yeah, on behalf of Department of Civil Engineering as well as from the GIAN side, I take this opportunity to thank you one and again, because in spite of your hectic schedule, you have accepted and then you have lended your support to the participants. I think the participants are still in the holiday mood. So, sorry. So, so I think I thank one and all again once again, uh, you for sharing your knowledge, and then I feel you are one such person, and then your papers who at the early times helped me a lot while I took my research forward, and then for the emerging contaminants such as nanoparticle, how the toxicity of those with respect to E. coli, and then everything and size dependent of silver nanoparticles. So I think the participants also would have got enough from your lectures, and then they will be taking the important key aspects, and then they will be applying for their research too. I strongly feel that.
That's wonderful. Yeah, thank you so much again. Yeah, from my side as well to you for the opportunity. It has been a pleasure and privilege to be able to present, although it was midnight, right? But I'm planning to sleep the entire Saturday, so
Okay,
um,
okay.
yeah, that's okay. But it has been a wonderful experience, and I hope our participant learned something. And hopefully, maybe in the future, we might be able to do some work together. So, looking forward to that.
Yeah, with this I think this was one such though it was supposed to be in the physical mode, I think with the, as Professor
Right.
Dubey also said, that physically we can able to have more understanding about what goes through in the minds of the participants, but still this is also one such challenge remotely that we need to take it up, and then we are taking up this challenge as well when we are delivering the lectures. So I think in future we will also put forward in another other way so that we can have a physical, or I can invite you, or in mutual collaborations that we can put forward, so that it will be helpful for all the people across the scientific community.
Sure, yeah, that absolutely sounds great. Yeah, looking forward to the opportunity in the future. And I thank all the participants as well for their time and for their patience and listening to me. And I wish all of them all the best.
Okay, okay. So thank you, Professor Loh. So with this, we come to the conclusion of this 5-day GIAN program, and it was one such program that was supposed to be in 2020, but luckily we have done it in
Right.
2022. So I thank the
Thanks.
participants again for their patience. And then with this, we will be closing the session, and then we will be going ahead as circulated to you all. We will be going for the multiple choice questions. Small questions will be of 15-minute duration, where you will be having 25 questions to sort out. I think it will be more or less the basic questions that we had discussed in this 5-day session, and then based upon that, your grade statement as well as the participation certificate will be forwarded. So I thank Professor Lok once again from Dubey sir side as well as my side, and wish you a happy weekend.
Thank you to you as well, and to Dr. Dubey too, and all the participants once again, and happy Holi to all of you.
Okay, yeah, happy Holi.
Thank you, sir.
Thank you. You have a great day. Okay.
Yeah, thank you.
And please try to stay in touch.
Yeah, definitely.
COVID time, but yeah.
Yeah, definitely, Professor.
All right.
Okay. See you then.
Have a good day. Bye. Bye, everyone.
Yeah.